How many times faster does a chip actually need to be before it stops sounding believable? For most of computing history, the answer was simple: a little faster each year. Smaller transistors, more cores, incremental gains, generation after generation. A team in Beijing just threw that entire pattern out. Not faster, not twice as fast, 1,000 times faster, and using 100 times less power to do it. Read that twice. It's not a typo, and it's not marketing. It's a peer-reviewed result, published in one of the most respected electronics journals on Earth. And the chip that did it doesn't even compute the way every device you own computes. No ones. No zeros. Something completely different. Here's the headline version. In October 2025, researchers at Peking University published a study in the journal Nature Electronics. They'd built an analog chip, not digital, analog, using something called RRAM, resistive random access memory. In direct testing against Nvidia's H100 and AMD's Vega 20, two of the most important chips in the entire AI industry, the exact class of hardware OpenAI used to train ChatGPT, this chip matched their precision while burning roughly 100 times less power. Push it further with additional optimization, and on certain tasks, it beat those same chips by up to 1,000 times. That number is what broke through into headlines everywhere. But the real story isn't the number. It's why almost nobody has built a working chip like this in decades, and why that suddenly changed. To understand why this matters, you have to understand the one thing every computer you've ever touched has in common: binary. Ones and zeros. On or off. Nothing in between. It's reliable. It's predictable. It's exactly why digital computing has dominated for the better part of a century. But it has a hidden cost. To do useful work, digital chips constantly shuttle data back and forth between memory and the processor. That shuttling burns energy. It burns time. For the kind of massive matrix math that powers modern AI, that cost adds up fast, and it's a huge part of why training a large language model can consume as much electricity as an entire small town uses in a day. Analog computing skips that shuttling entirely. Instead of ones and zeros, it processes information as continuous electrical signals directly inside physical circuits. No back and forth. In theory, dramatically faster, dramatically less wasteful. The problem is just as old as the idea itself. Continuous signals drift. They're messy. They're imprecise. Temperature changes them. Electrical noise changes them. Time itself changes them, as components subtly degrade. That's exactly why analog computing got abandoned for most of the last century, even though it's actually older than digital computing by 2,000 years, tracing all the way back to mechanical devices like the Antikythera mechanism, built by the ancient Greeks to track astronomical cycles using nothing but gears and physical motion. Engineers didn't give up on analog computing because the idea was bad. They gave up because nobody could make it trustworthy. A digital chip tells you, with total certainty, whether a switch is on or off. An analog chip only ever gives you an estimate, a signal that has to be interpreted, and interpretation is exactly where errors creep in. For decades, that single weakness was enough to bury an entire branch of computing that, on paper, should have been faster and more efficient than anything digital could ever offer. So what changed? The Peking University team built their chip from RRAM cells arranged into two circuits. One does a fast, rough first pass. The second refines it, cleans up the errors. That two-stage trick is the whole insight. Instead of demanding one analog circuit be perfectly precise on its own, which is where analog computing has always failed, they let a fast circuit guess, and a second circuit correct the guess. Think of it like a sculptor working in two passes. The first pass roughs out the shape fast and imperfectly. The second pass, slower and more careful, chisels away exactly the errors the first pass left behind. Neither step alone would be good enough. Together, they produce something neither digital engineers nor previous analog researchers had managed. A result precise enough to actually trust. Tested on real problems. Matrix inversion for wireless communication systems. The kind of math behind 6G. Partial differential equations used in weather forecasting and fluid dynamics. The same category of calculation that supercomputers spend enormous amounts of time and power grinding through today. Matched digital-level precision. Used 100 times less power doing it. Optimized further. On those same tasks, it hit 1,000 times faster. Picture what that actually looks like in practice. A calculation that might take a top-tier Nvidia GPU a full second to complete. This chip could, in theory, finish in 1/1000th of that time, while drawing a tiny fraction of the electricity. But here's the question that actually matters, and it's the one most coverage skated straight past. Does beating Nvidia's H100 by 1000x on a math problem mean this chip is about to replace the GPUs training every AI model on Earth? Or is there a much bigger gap hiding behind that number? Let's be precise about what actually got proven here, and what didn't. It proved that analog computing can now match digital precision, using 100 times less power. That's the real, demonstrated core result. It's why Nature Electronics accepted the paper in the first place. Because precision, not speed, has always been analog computing's fatal flaw. And this is the first credible peer-reviewed evidence that the flaw might actually be fixable. It did not prove that this chip can replace a general-purpose GPU across every task a modern AI data center throws at one. The 1000x figure came from specific optimized tests on specific tasks. Heavy matrix and signal processing problems. Not full-scale AI model training the way an H100 actually spends most of its life. Running an enormous variety of workloads, from language generation to image recognition to recommendation systems. The researchers themselves framed the 1000x number as something the chip could achieve with further improvements. Not a blanket number. A demonstrated ceiling on certain work, under conditions the researchers specifically optimized for. And this isn't a random isolated result either, which is worth knowing. The precision problem this chip solves has been the central bottleneck of analog computing for decades. Multiple teams, multiple countries, tried and mostly failed to crack it, since analog computing's earliest revival attempts in the mid-20th century, when engineers briefly experimented with analog computers for tasks like flight simulation and artillery targeting, before digital systems overtook them completely by the 1960s and 70s. This team didn't just get lucky once. They specifically targeted the exact failure point that's killed every previous attempt, and built a two-circuit fix for it, grounded in a materials approach, resistive memory, that itself has only become reliable enough to work with in the last several years. So here's the honest scoreboard. Nvidia's H100 is a general-purpose AI accelerator. It trains language models, runs vision systems, handles recommendation engines, all using the same reliable digital architecture, at massive commercial scale, backed by years of software, developer tools, and infrastructure built specifically around it. Every major AI lab on Earth already knows how to write code for it. This analog chip, right now, excels specifically at matrix-heavy, signal processing style problems. Real, valuable, not yet universal. There's no equivalent software ecosystem built around analog RRAM chips yet. no widely adopted programming framework, no decade of accumulated developer experience. The distance between "we proved this beats an H100 on specific math" and "this replaces H100s inside real data centers" is still measured in years of engineering, not months. But here's why chip engineers everywhere are still watching this closely, because the specific problem this chip solves happens to be the biggest hidden crisis in AI right now. Every large AI model has to constantly move data between processing and memory just to generate a single response. That movement costs energy. It costs speed. It's such a fundamental limitation that it has its own name in the industry: the memory wall. Data centers running these models are consuming staggering, rapidly growing amounts of power, straining electrical grids in multiple countries, to the point where tech companies have started signing deals to bring entire nuclear power plants back online just to keep up with AI's appetite for electricity. Raw computing power stopped being the only bottleneck a while ago. Energy became one too, and in some regions it's already the harder constraint to solve. A chip that matches digital precision at 100 times less power isn't just an academic curiosity dropped into that environment. It's aimed straight at the most expensive, most urgent problem the entire AI industry is currently fighting. Even a partial solution, applied only to the specific matrix-heavy calculations this chip already excels at, could meaningfully reduce the energy footprint of the exact workloads currently straining data center power budgets the hardest. There's a second detail that matters just as much, and it's easy to miss if you only skim the headline number. This chip was fabricated using a completely standard CMOS manufacturing process. The same basic process the global semiconductor industry already uses today, in the same kinds of factories, with the same kinds of equipment. That's not a small footnote. Plenty of brilliant lab breakthroughs in computing go absolutely nowhere specifically because they need exotic, unscalable manufacturing techniques, specialized materials nobody can produce at volume, or fabrication steps that only exist inside one research lab's custom equipment. This one doesn't. The path from impressive paper to something you could actually manufacture at scale is dramatically shorter here than for most research breakthroughs, precisely because the factories capable of building it already exist. So where does this actually go from here? The next milestone to watch for is the one that always separates a lab result from a real product: broader task coverage. Right now, this chip's advantage is demonstrated on matrix inversion, wireless signal processing, and specific differential equations. Expanding that range, while keeping the same precision and efficiency, is the difference between great for wireless and physics simulations, and could actually sit inside a next-generation AI data center, doing the broader range of work an H100 handles today. Also watch for independent verification. Because this chip used standard CMOS fabrication, scaling up production for outside testing is realistically much faster than for more exotic lab technologies. External labs with no stake in the hype, including ones outside China with every incentive to find flaws rather than celebrate the result, could start testing this sooner than most academic breakthroughs ever get independently tested. That verification process, more than any press release, is what will ultimately decide whether this becomes a footnote or a foundation. And there's an obvious near-term path already being discussed among researchers: edge computing, wearables, IoT sensors, places where the 100x energy efficiency matters enormously, even without needing the full 1000x figure on every task, and where the narrower range of tasks this chip currently handles well happens to overlap heavily with what small, battery-constrained devices actually need. That's usually how disruptive chip architectures actually enter the real world. Not by dethroning the biggest, most demanding data center workloads first, but by proving themselves in smaller, power-starved devices, building manufacturing experience and real-world credibility, and scaling up from there, one product category at a time. Nvidia isn't standing still either. Their own roadmap already targets cutting AI's energy costs directly, because their own leadership has said cost and power, not just raw performance, are now the industry's central fight. If analog computing genuinely proves out at scale, expect major chip companies everywhere, not just in China, to start seriously exploring hybrid systems that combine analog efficiency for specific tasks with digital reliability for everything else, rather than dismissing this as a one-off research curiosity that stays confined to a single lab in Beijing. There's also a broader pattern worth naming here, because this isn't happening in isolation. Chinese research labs have been pushing hard across multiple, very different corners of chip architecture at once. This analog RRAM approach, alongside entirely separate work on next-generation memory storage and novel transistor designs. Some of that broader effort is explicitly framed around finding paths that don't depend on the most advanced, most heavily export-controlled manufacturing equipment, since Chinese fabs have faced real restrictions on accessing cutting-edge lithography tools in recent years. An approach like this one, grounded in materials science and circuit design rather than in shrinking transistors to ever smaller nodes, sidesteps that entire bottleneck. It doesn't need the newest lithography machines. It needs clever circuit design and materials that are already well understood. That's strategically significant well beyond this one specific chip. So let's put this together, because both the hype and the dismissal are missing the real picture. The hype version, China just made Nvidia's H100 obsolete, goes too far. This chip hasn't replaced general-purpose AI training GPUs, and its 1000x figure applies to specific tasks under optimized conditions, not universally across the enormous range of work a modern data center actually demands. But the dismissive version, it's just one lab paper, it'll go nowhere, badly underestimates what got proven here. Analog computing has fought the same precision problem for the better part of a century, defeating engineers across multiple countries and multiple decades. This team, in a peer-reviewed paper, in one of the most respected electronics journals on Earth, demonstrated a real working path past it. Built using manufacturing that already exists at commercial scale, not some exotic process that only works inside one lab. That's the real story underneath the viral number. Not proof that Nvidia's been outbuilt. Proof that an entirely different way of computing, one the world mostly gave up on decades ago, just became viable again, at the exact moment the AI industry is desperate for anything that solves its energy crisis. Let's run through the numbers one more time. 100 times less power, at matched precision. That's the core proven result. 1,000 times faster, on specific optimized tasks. That's the ceiling they've demonstrated so far. Standard CMOS manufacturing, meaning this could actually scale without needing new factories or exotic materials. 2,000 years, how far back analog computing's history actually goes. 3 to 5 decades of failed precision attempts, finally cracked by a two-circuit design nobody had quite combined this way before. October 13, 2025. The day one of the oldest assumptions in computing got a real peer-reviewed crack in it. If this helped you understand what actually happened here, not the exaggerated version, not the dismissive version, but the real science and the real stakes, hit subscribe, because we're going to keep tracking exactly what happens as this moves from a research paper towards something real. Thanks for watching. We'll see you in the next one.